So we talked about finding a minimum or maximum on a local level, kind of zoomed in on our graph, but now what if we zoom out and talk about absolute extrema? What is the absolute largest output and what's the absolute smallest output for our function? And with this, we really need to pay attention to so many things at the same time. What's the interval that we're looking at? Are there any discontinuities within that interval or asymptotes? So we need to be careful of a few scenarios here. So absolute minimum will be the absolute smallest output value. Absolute maximum will be the absolute largest value on the interval that we're looking at. And these two graphs I like as examples of kind of how these come through. So the absolute maximum in this first case would be occurring at x equals 0. So it would be this coordinate 0, 2. This would be our absolute maximum. Because in terms of y coordinates, it's the absolute largest. Now, notice that this has no absolute minimum. So we can see this lowest value right here, except that's empty. There isn't a coordinate there. So technically it's like down at negative 1.9999999. That's where our minimum is, but we can't define it. Like I could have just kept saying nines forever and still wouldn't be the closest. I'd have to keep going and going and going. So with this, we can't define an absolute minimum. So with that, we would just say there is none. This case here, what we can see is an absolute maximum up here at the coordinate 4, 4. Absolute maximum. And then our absolute minimum would be a coordinate showing up right here at 2, 0. And notice that that is a critical point. That is a point where our first derivative would equal 0. And that would be our absolute minimum. So when we look at these, we want to look at the endpoints of our functions. We also want to look at the critical points, and then we also want to be careful of any discontinuities occurring. If this was a solid circle, say that was defined, then it would be an absolute minimum. At 2, negative 2, then it would be an absolute minimum, but with that open circle, it is not. So if it was a jump discontinuity where the top one was undefined, but this one was defined, we'd be okay. Okay, so finding absolute extreme. What we're going to do is find our critical values. We're going to evaluate our function at each critical number. We're also going to evaluate our function at each input, and then we do a comparison of the y coordinates. So I'll show you how I like to go about these. Actually, I'm just going to divide these up so I can see a separation between them. So where I start is by building a table. I put a table off to the side of my work where I'm going to collect x values along with their function outputs. And the first values I throw in there come from the interval. I'm going to have 0 and 4. Then from there, I'm going to add to the table using critical values. So now I'm going to go over here and find critical points. So I'm going to take the first derivative for 3x squared minus 6x. I'm going to see where that equals 0. I'm going to factor out a 3x for an x minus 2. And I'm seeing x equals 0 and x equals 2. So I'm going to go to the table, and my critical points, I have a 0 and a 2. It doesn't make sense to list 0 again, so I don't need to. So 2 is my new unique value. Something I also need to see is I need to make sure it's in the interval, because we might get values that are outside the interval and we don't care about those. So if this was a negative 2, we wouldn't include it on the table. We would just look at the endpoints then. But for this case, it is in the interval. It is a critical point. We just don't need to include repeats. Okay, then from there, I'm going to evaluate my function at each of those values. So I'm going to look at f of 0. So 0 cubed minus 3 times 0 squared is just 0. If I look at f of 4, I'm going to have a 4 cubed minus 3 times 4 squared. And that's going to be 3 times 4 squared is 16. So we have an output of 16 there. And then f of 2. So notice I'm plugging these into the original function. So I want the y coordinates that would be graphed with them. So let's see. 2 cubed minus 3 times 2 squared. It's a negative 4. Okay, so once I have my table, what I'm going to do is compare the outputs. I want to find which is the absolute largest output. And in this case, that's going to be the 416, which tells me that's going to be our absolute maximum. And then I go through and look for the absolute smallest y value, which will be that negative 4. And that tells me this will be our absolute minimum. So we get our 2 coordinates, and it just comes down to only look at the y values, and it's just what's biggest, what's smallest. Because in terms of our graph, that's what matters. It's what's highest up versus what's lowest on our graph. Okay, let's go through a few more of these. Okay, so something I want to be careful of here is that this is defined at x equals 0. We'd have a vertical asymptote. However, our interval doesn't include 0, so we should be okay. But just again, take a look at the function, think about where it's undefined, and any issues that might cause. Okay, so this is coming from an x plus x to the negative 1. So, oh sorry, I said this with the first one. I start with my table. I like to just get my table going because that's where everything will be collected. Let's see, for our interval, we have a 1 and a 5, and then I just need to add any critical values. So, taking the first derivative, we'll have a 1 minus x to the negative 2, and we want to see where that equals 0. Okay, I'm going to add the 1 over x squared to both sides, multiply both sides by x squared, take the square root of both sides, and never forget that we have the plus or minus when we do that. So we're going to get a plus or minus 1. So what I'm getting to add to the table is a positive 1 and a negative 1. Now the positive 1 is a repeat, so we don't need that. Negative 1, it's not in the interval, so we don't need that. So we only end up with our endpoints of 1 and 5, and that's totally fine. So no matter what, we should at least have the endpoints, and then anything else that we can add on is good. Okay, f of 1 is going to come from a 1 plus 1 over 1, so that's 2. And 5 is going to come from 1 plus 1/5, so 1.2. So our smallest is going to be the 1.2, and our largest is going to be the 2. So this will be our absolute max, and this will be our absolute minimum. Okay, on an open interval, that means we don't have any endpoints to add. So all I'm going to have on this table are critical points. So let's take our first derivative for 3x squared minus 4x, see where that equals 0. And we're going to have x equals 0 and x equals 4/3. So we're looking at 0 and 4/3 as our 2 values on the table. If I plug in 0, that output will be 0. 4/3 is a little trickier. I'm going to throw that in the calculator. So 4/3 cubed minus 2 times 4/3 squared. For negative 32/27, let's go decimals here. Negative 1.185. Let's say that. All right. Absolute minimum, absolute maximum for largest y value and smallest y value. Okay, and that's how we're going to find our absolute minimums and maximums. Just make a table of values with our endpoints as well as any critical points that we can add on that fit that interval.